can be safely said that we would be living with two types of universe. The one of dark matter, and the one we observe through light. One does not exist without the other. This duality is false, but it would be established by the way in which we interact with dark matter, as we depend on our memory to do so. To see the particles that make up dark matter, we must first illuminate them. This lighting takes time, and, unavoidably, disturbs the particle. You cannot know where in space the particle is, or at what point in time it would be existing. It is concluded that the act of illuminating a particle would determine its existence and its relative motion. So, dark matter can and should be static, at least until the moment it is illuminated. This is where the Copenhagen interpretation, proposed by Niels Bohr in 1927, comes in. It places the observer as a fundamental part of quantum mechanics. The properties of light as a wave or a particle know when to appear, because the experimentalist effectively tells them what to do. This detail is disturbing and has been tenaciously denied by Einstein and other physicists. For them, a particle continues to exist even if we are not there to see it. These days, the view of Copenhagen is treated more seriously. In any case, everything indicates that the movement of particles depends on the observer and his memory, since the movement does not exist outside of time. As we would see that particles always live with delay, or with the appearance they had in the past, we fall back into the false duality of the universe. Let's start from the hypothesis that the real particles would be static, and would compose a universe that is also stationary. This kind of universe was supposed to be timeless, so it couldn't be reached by our memory. The necessary illumination of the particles, which would allow us to verify their existence, would be done in two stages. In the first, the light would be packaged or co-induced, a process that, according to quantum mechanics, would not require time. Thus, the particle would remain invisible to us. Even though this cannot be proven in practice, the packing of light should simulate the existence of a negative curvature in the space around the particle. This is because it has already been demonstrated by physics that the formation of the quantum does not require a measurable time. In order for the movement of the particle to become visible to the operator of the quantum system, the arrow at time would have to undergo an inversion in its direction at the same time that the light was scattered in the form of a photon. This inversion movement of the time arrow would isolate the particle, preventing the observer from seeing it directly. For this, he would depend on the messenger of the particle, the scattered light. If, in the first phase of photon formation, space occurred negatively, stretching like a spring, and retaining the information, it is understood that it should be contracting in the opposite phase, or losing curvature. This detail would justify the fact that we are recording the stretching of light and its redshift in a time-phased manner. This can be easily seen in the fact that when the spring of space stretched between two particles, the stretching would be followed by an increase in elastic potential energy. There would be the generation of tension between the ends of the spring and deceleration of the movement of the particles. But, when the light was scattered, the observer would, finally, have access to the information about the stretch, and he would see the particles speeding up, even with the light shifting towards the red. The two events would belong to opposite phases, and mutually exclusive. If you could see the spring stretching in real time, which it wouldn't, in practice, you wouldn't be able to see it contract simultaneously. The use of light to visualize the particles puts them in continuous and relative motion due to the exclusion of direct access to the quantum formation phase. As this phase does not require time, the opposite phase, the contraction of the spring, is the only one that allows the observation of the moving particle. Therefore, it appears to be continuous, even in the presence of the redshift of scattered light. The space of the particle universe appears to be flattening out continuously, with visible matter gradually and continuously losing density. One of the problems at the illumination of particles' presence is the fact that the light waves emitted or reflected by the particles are circular. As they moved away from the center, the waves would overlap over time, forming a straight cone. Particles that were described by this type of circular wave could not move towards or away from other particles. Under these conditions, an illuminated electron would always be at the same distance from the nucleus of the atom, rotating around it with constant speed and acceleration. That is, the depth of the curvature of space around the particles would remain constant over time, which would plaster the entire atomic system. Before making the quantum leap from its current level to a higher energy level, the electron disappears. That is, it cannot be detected in any way in the space between these two independent levels. This is where the cat's leap would take place. The space between levels would be curving negatively, retaining the light and the information it carries. When the electron abruptly appeared at the most energetic level, the inversion of the time arrow would have occurred, and so, the consequent scattering of the photon used in its illumination. At this point, space would already be losing curvature, but the light would have to cope with its previous stretching with a delay. Therefore, the scattering of light should be followed by an increase in the wavelength of the scattered light, predicted in the photoelectric effect. Our dependence on the illumination of particles eliminates the question of the distance between them or the time that separates them. This would apply to both the infinitely large universe and the subatomic level. It is due to the fact that we depend on the local scattering of light to describe any kind of movement. Your telescope would be useless if the light of a distant star were no longer available to you to be followed only in the direction of your past. In this case, the past is an illusory concept, as it would depend on the scattering of light near us.